So in this video, we're going to talk about an application of E in optimizing the product of the lengths, essentially maximizing the multiplication of divisions of a number using E. And this is just a bit of a fun challenge. E shows up in a bunch of places, and we could talk more extensively about that. But I think this is a nice little optimization problem, and E does show up quite a bit in optimization. So I figured I'd just take a crack at this. If we wanted to take a number, say 20, okay, let's take 20 and split it into equal numbers. So let's say 20. We can think of 20 as 10 plus 10, right? We can also think about it as 5 plus 5 plus 5 plus 5. That's two different ways we can think about it, or here's another one, 4 plus 4 plus 4 plus 4 plus 4. Now, what if we split this number and then we multiply its parts? Well, 10 times 10, right? If we replace these addition symbols with multiplication symbols, right? And maybe I'll just do that like so. If we do that, then 10 times 10 is 100. 5 times 5 times 5 times 5. If you plug this into a calculator, this is 625. 4 times 4 times 4 times 4 times 4, that is 1024. It turns out that the closer we get the size of these individual parts, the closer we get those to E, to 2.71828, the larger the result of multiplying those parts. That's pretty interesting, right? It's just another emergent property. Now, we could take the approach of trying to estimate E through this, but let's instead let's think about this a little differently. Let's just write a function that figures out the best number of equal-sized parts for maximizing the multiplication of those parts. And let's not initially use E to do this. So let's do this in Python. I'm going to arbitrarily, just initially, I'm going to arbitrarily set the minimum number of pieces to 2. And I'm going to haphazardly set the maximum number of pieces to the floor of the number itself, okay? Since the number divided by itself will be 1, and all those sides multiplied would equal 1, right? Like if we split 10 into 10 parts and multiply 1 by 1 by 1 by 1 10 times, that would be 1, right? And that's obviously not the optimal value. Given our prior knowledge regarding E as the optimizer, as the optimal value, having parts of magnitude 1 is obviously not optimal. So I'm just gonna write this directly. So the product of the lengths dictionary. We're gonna give it a number, such as say 10, and if the number is less than or equal to 0, obviously that's not going to be good. I'm just going to return -1, and in all other cases I'm going to pack in a dictionary, as we've been doing. Okay, so I'm going to say for the number in the range, and let's do number. I'm going to call this n pieces. Why not? In the range from 2, right? Because we're assuming at least 2 pieces, to the integer value of the number. And I'm saying int of num because we could give this a float, right? We could give this a float, and that float would be valid, right? We can cut up a continuous value into equal pieces. You know, for our purposes, we can do that. Okay, so each piece length. So if we've got 2 pieces, the piece length is going to simply be the number, the original number, divided by the number of pieces, right? 10 divided by 2. Easy. And then we can make the product of the lengths. That's going to be the piece length square to the power of the number of pieces. So at that point, I can say d sub n pieces is going to get the piece length. I'm going to give this a tuple where I give it the piece length and the product of the lengths. This is going to make it a little challenging to walk through, but it's going to give us a lot of information. Okay, so now I'm just going to say for the number of pieces, right, I'm going to traverse this dictionary. For the number of pieces and the result, which is a tuple, in the product of lengths dictionary. And let's give it the number 27. Dot items. Let's print the number of pieces, right? That's interesting to us. Let's print the piece length. Am I spelling piece correctly? Shoot. Let me just check that. Okay, good. This this word never looks spelled correctly to me for some reason. Yeah. Okay. So we'll do piece length, and that'll be that's the first value of our tuple, res sub 0, result sub 0. And then let's also do the product of the lengths, which is going to be res sub 1. Okay. Let's take a look at this, and keep in mind this is for the number 27. Okay. There's kind of a lot of information here, but we're looking for some optimal, some highest value of the product of the lengths. And if I'm scanning through this, 6, 16, 39, 90, 195, 2603, okay. For 4,000, 6,000, 13,000, 16,000, wow, we're getting, where are we, 10 pieces? So it looks like right here, we've got the maximal number of pieces, 10 pieces, which, look at that. That's a piece length of around 2.7. And that gives us a maximum product of the lengths. We could put in any number of numbers here, right? Let's say, I don't know, let's put in 53 and see what we get. I'll have to scan through this a little more, but the way that I'm going to scan through this, actually, I'm just going to look for 2.7 something and see how that's doing. And yeah, indeed, that is the best that we're doing right here with this product of the lengths. That is a massively large number. That is our closest value to E when we're looking at it here. So let's take this a step further, and let's make a dictionary where we observe for different lengths, and we're going to use discrete values here for different lengths from some low number to some high number. Let's look at through the optimal approach that we've taken. Let's look at the optimal lengths. So I'm going to go, this is optimal length dictionary. I'm going to go from some low number to some high number. And we have a dictionary. And I'm going to say, well, for num in range, we'll go from the low numbers to the high number plus 1, right? We'll include it. The I'm going to get a dictionary out, the num dictionary. I'll just call it that. And I'm going to say this is the product of the lengths dictionary of the number that we're looking at that's currently in this range. Okay, and then we're going to get an optimal product. We're going to set an optimal product, optimal n pieces, and an optimal piece length. Okay. I'm going to initialize all of these to -1. Obviously, those -1s don't mean anything there. I'm going to replace them with better values. Now, we're trying to optimize for the optimal product. And I'm going to do that in a boneheaded way. I'm not going to search for the max. I'm not going to do anything like that. I'm going to show a kind of generic accumulator procedural way because that is kind of a simple way to conceptualize it. A very classic, simple way to conceptualize it. So I'm going to traverse this dictionary, numd, and I'm going to say if tup sub 1, right? And remember, tup sub 1 is our product of the lengths, which is what we're optimizing for. If tup sub 1 is greater than the optimal product, then the optimal product is going to get tup sub 1, right? Simple logic. And our optimal number of pieces, that's just going to get num pieces. I'm just updating each of these. And the optimal piece length is going to get tup sub 0. So I populate these, I update these every time we see an optimal product that is, every time we see a higher product in tup 1. Okay. And then at the end of this for loop, I can just populate d. I can say d sub num is going to get, and I'm going to do a dictionary for this. You know, why not? Optimal n pieces. And notice I can store a dictionary as a value for the key in a dictionary. That's what I'm doing here. And this is just the optimal n pieces. And the optimal piece length is going to be the optimal piece length. And is that enough? Is that all I want? How about I add another value in here? Let's do optimal product as well. And obviously that can just be optimal prod. Okay, I think that should work. And at this point, we can return the dictionary. And the for loop here, you know, let's just traverse this. Let's do for num piece length. Right, because each of these values is a key. Why don't I do, we'll call this for num and dictionary in the optimal lengths dictionary, and we'll go from, let's just go from 10 to 30 and see what these look like. Let's print f string. How about we do this? Let's do the num and colon, and then we'll go for key value in DCT, and let's just ensure that those are in the same order that they should be, but I just like doing that. Let's print the f string. We'll put a tab in there, and we'll do the key and the value. And hopefully we'll get some reasonably nice output from doing this. Okay, let's try that out. Okay. So if we're looking at this, optimal number of pieces for 10 is 4 pieces, and we have 2.5. For 11 is 4 pieces, 2.75, right? And then for 12 is 4 pieces, and we have 3. And, you know, keep in mind here that the number of divisions has to be, the optimal number of pieces has to be discrete, right? These values, 12, that number doesn't have to be discrete. And the optimal piece length is not discrete, obviously. It's a length, right? But if we look through these numbers, 2.5, 2.75, 3, then 2.6, 2.8, 2.5, it might already occur to you that we could go through and average these optimal piece lengths as we increase the number of divisions, or sorry, as we increase the size of these, and we are likely going to get something that more and more reasonably looks like E, the greater our value of the more observations we look going up to infinity. And something you might also notice here is we are going to get recurrent values of these. We could even count these, and I think that can be interesting as well. I'm not going to do either of those things. I'll leave those to you. If you want to rewrite this, rewrite something of the approach I've done here in order to determine in order to estimate E. Think about how to do that. I think that's an interesting problem, and I can think of a way to do it offhand that I think would work, but I'm not even going to try it. And I'm hoping someone out there will try it and post a link to a gist on GitHub and say, hey, I did it like this. I think that would be great. Okay, so let's do another one of these. I'm going to comment this out, and instead of doing 10 and 30, let's do 100 and 300. And if you look at these values, some of these are looking very, getting more and more E-like. And when I say that, some of them are. Now, you could do an analysis of the discrete value against how close, right, the distance E is from our optimal piece length. That's another thing you could do. So, sky's the limit in terms of what you can experiment with here. I think there's a lot of fodder. Okay. Here's the thing, though. If you want to optimize for the product of lengths, given what we've seen above, we can comfortably do so with a very simple approach. We don't need to do this whole product of lengths dictionary and pull out an optimal lengths dictionary. We don't need to check every value to look for the greatest product of lengths. Instead, we can divide any given number by E and round it. So let's do that. And then let's compare the dictionary we get out of that to our previous dictionary and see what we encounter. So I'm going to call this an optimal product of lengths, divs for divisions, and we'll put in a number, right? We put in 10. We can just return the rounded value of that number multiplied by 1 over E. Okay. So I think of this as a closed approach, right? We've got this closed approach. We're not searching for something. There's no conditional in here. We're just getting out a value. So I'm going to call this dictionary. I'm going to call this optimal lengths closed dictionary. And we'll go from a low number to a high number. D is going to get, we're going to instantiate D we'll say for a number in range, we'll go from the low number to the high number plus 1. And the optimal number of divisions is going to be this, right? The result of this operation. Oops. Now, you might be asking, why didn't you just take this and put it here directly? I don't have a good answer for that. I think normally I like to have a separate function here because we could utilize this function outside of our dictionary building function. That's, well, I guess that is a good reason. So I do have a reason. So d sub num, and we'll just, again, make a dictionary here. So we're going to store a dictionary in relation to this, and I'm going to copy this and modify it for use here. So the optimal number of pieces is our optimal divs. The optimal piece length is going to be the number over the optimal divs, right? And then our optimal product is going to be our number divided by the optimal divs raised to the optimal divs. Right, that's the optimal number of divisions. Oh, wait a minute. Sorry, yes, num over op divs. That'll give us our piece length. Yes, okay. Hopefully I'm thinking about that correctly, and we can just return the dictionary. So one of these calls should be fine. I can just change, hopefully I wrote this in a way where I can just change the name here, num optimal lengths closed dictionary. Let's do that. And let's see if that works. I believe that worked. Now there's a chance that these two dictionary that these two approaches don't lead to an equivalent dictionary. I think they're equivalent enough, likely. So, but let's just check, right? I'm going to, let's do this. I'm just going to compare the dictionaries themselves, and if they're not equivalent, we can just throw in a single value and see why they are not. Okay, so we're going to put in 10 and 30, and then I'll just copy this because it's essentially the same, and get rid of this word closed. So we should be comparing the function I just wrote here with the function above here. So let's see if these match up. They do. Okay, that's a little surprising considering that under the hood there's storage. There's storage of float numbers and things like that. But these are pretty determined. They should store in the same way even though they're floats, and they should have the same kind of rounding error either way. So maybe I shouldn't be too surprised, but I am a little surprised given the complexity of the dictionaries. Awesome, we get true. Yeah, so I'm just gonna wrap up here. Maybe I'll make more videos on E in the future, but we've explored E quite a bit here. Hopefully this gives some basis as to why we might see E pop up in so many places as this emergent property, as this constant in the universe. I'm sure I'll talk about E in other videos in relating the Poisson distribution back to the binomial distribution. At any rate, I hope this has been interesting. I know there's a lot here, but this is just, you dig into a problem and you get a feeling for it, and you end up understanding it a lot better. So I encourage you to use Python to explore mathematical notions. I gave a couple suggestions of things that you might do in terms of this problem in expanding your understanding. And yeah, put in the comments if you have any other relationship that describes E, any other place where you think it's really cool that E emerges. If you show me something that is particularly interesting, I will make a video on it and I'll add it to this playlist because, this stuff's fun. And appreciate your time. Thanks so much for watching. And I'll see y'all before very long.